Hello guys, welcome to Digitronix Nepal's online course on Verilog SGL programming for beginners. This course is prepared along with Xilinx ISC design suite, so you will practice our lecture session in your Xilinx ISC design suite. Let's begin to our current session. So we already have completed our section 1 and section 2, so this is section 3. In this section we are going to talk about conditional statement in Verilog. So first of all, we will talk about what are the conditional statements and what are the type of conditional statements are available in Verilog. So this section is further divided into 4 lecture sessions. So first is basic concept of conditional statements. Second lecture is using always block. Actually, while using conditional statements, we need to insert always statements or called as always block, which actually signifies the insertion of sequential statements in the Verilog program. Actually, conditional statements are sequential statements, so those sequential type of conditional statements must be included with always block. And we will to talk about if statement in lecture 3, and lecture 4 we have case statement. Let's begin from lecture 1. So this is the overall learning objectives of this section 3, conditional statement with Verilog. You will be able to explain about the conditional statements in Verilog, then after able to define and explain about different statements and conditional statements like if, case, and how to use always block from this session. So while talking about conditional statements, actually conditional statements are those statements which actually provides the result in zero or non-zero form. If the condition is true or condition is satisfied, then the statements will give us true or high value. So condition satisfied means high, and condition not satisfied means condition false means zero. So this is the basic logic of conditional statements in programming language. So we can see if the input satisfies the condition, then output will be high, or non-zero, else output will be zero. So these conditional statements will be using or will be used in any programming language highly. So we can see flow diagram of conditional statements. Actually, there is a start point, then we will check the conditions. If condition is true, that is satisfied, means yes, statement 1 will be displayed, else statement 2 will be displayed. So this is the basic logic of conditional statements. Let's talk about two types. Means if statement, which also include if else statements. We can use like a multiple ladder if, else, if else, if else. Like we have another case statement, and aside of conditional statements, like looping structures are also available in Verilog. Those are while loop and for loop. We will talk about loop in another session. So in this session, we have prepared about if statement and case statement mostly. So let's talk about the if and case. Those if and case are sequential statements because those statements run in sequence, means one after another. So those sequential statements must be included in always block. So this is the assignment in this section, which will be included in quiz of this section. So you will see the quiz after this video session. So we should know about always block. Means in our lecture 2 we have always block. Always block is the modeling methodology, which include actually the different sequential statements inside of it. So we should also define about the sensitivity list of always block. Actually, always block is the statements, collection of statements which needs to have sensitivity list. Means sensitivity list are those parameters which always block is sensitive on. So this is the main logic of always block. So we can see here always block. Always is a keyword, and we will write always space a @ Then after we have a small bracket and sensitivity list. Actually, sensitivity list includes different type of parameters like ports. Mostly we include input ports in sensitivity list. Then the small bracket has been closed. Then after always we have begin and end statement. So between begin and end of always we write different sequential statements like if, case. So we have basic logic of always. So we can also use curly bracket instead of a small bracket in the conditional statements. So we can see one example of always block. We will also test this type of example in our Xilinx IC design suite. So let's talk about example. Example actually simple bitwise not example. So we have module bitwise not, which have input of 2-bit A in and output of 2-bit A out. So we can declare multiple input or output ports in square bracket. Means square bracket, the top bit of value, that is MSB is to LSB. Means if we place 4 is to 0, that shows 5 bit of that port. So we are going to actually make a bitwise not of input and gives to the output. So we also have a register defined in our program module. So register is similar as of output port. So we can see in another line, another statements, that is always at the rate, which is the always block starting. So A in is the variable or sensitivity list of this program. Means A in is the input, which is sensitive to the always block we are using on. So we can see here always block is begin and always block is end. Between begin and end we have the main logical statement, means sequential statement, which is actually A out calls to not of A in, which is actually bitwise not of input. So after that we can end the module. This is the basic logical syntax of always block using always block. So we will do one example in our Xilinx IC design sheet. Let's begin with another slide. So this is the explanation about how we use always block in bitwise not program. So you already know about that basic concept of using always. So let's start with basic logic of always in Xilinx IC design suite. Let's open IC design suite and we are going to write a program with always block. So let's create a new project. Actually 6131. Okay, let's do next. You already know about how to create a new project and how to add a Verilog source. So I'm going to do it fast, just writing always, and I'm going to do simple logical gates like NOR gate, which have input of A, B and Y, and I'm going to take the multiple inputs and multiple outputs, actually 2-bit input and 2-bit output. So you can use this boss feature on define module section. So we are going to write this program is dependent on A and B. This is the basic program for NOR include in always. I just want to tell you something, because while we use multi-bit ports, so we need register. We need to define register Y. So actually registers doesn't have any orientation like port orientation. So registers are just a simple memory element which can store some results or any operation. Try to show you some different style of Verilog program, which is actually in Verilog 1995. So in 1995 we actually declare port orientation in letter section. So in module we only have different type of port names only. Then after we close the module declaration, then we have orientation of ports in input and output statements. Then after we can define register. Actually, this output port doesn't hold any results, so we need to have some register which can store that result and show up in output port. So for that we have similar name of register as of output port and similar bit width, which is actually 2 bit. So we talk about always block. So always block is started always at the rate a or b, means this a or b are ports, input ports, which are sensitive to the upcoming statements. So always block has been begin. So after that we have y equals to, this is actually XOR, and you might be confused about why here is no assign, because assign is a procedural statements. We don't need assign statements while using always block. So you must be clear about while we use always block there is no necessity of assign. But if you are not using always, then you should have assign. So we can't left this type of statements without always. So always block has been ended, and after module has been ended. This is the basic logical concept of writing program for XOR with always block. We can even simulate this program very fast, so we can see here. And thus we need to add simulation test fixture. Then after we can add different logical. So we can see here the simulation of NOR gate. You already know about how to simulate this type of Verilog program. So I will just show you very fast. After this simulation, we will talk about if statement and case statement. So let's see the waveform for XOR. Actually, we have did XOR, which is like actually we can see here multi-bit inputs and multi-bit outputs also. So we have A and B as input and Y as output. So our result will be displayed on Y. So if actually what happens here is we have this operation actually did bitwise ORing. So we have some introduction about operators, bitwise operators. So this is the OR operator, which will OR bitwise, means XOR bitwise. So LSB of A will be ORing with LSB of B, and MSB of A will ORing with MSB of B. So result will be displayed on corresponding bits of output port, while we have used a register for storing that value. So we can see here A 00, B 00, and we have output of 1 because we have did XOR bitwise and bitwise. So we can even see different logical statements, logical states. 0001, 0001, it will be that. And this is the overall result of XOR multibit. Now we must continue on always on if statement. Actually, if statement is the logical statements which actually give the result of 0 or non-zero form. So we all know about. So we also need register, defining a register for any output ports. So we have register F. Here is a short example of how we can use if statement. So we should include always block while using if statement, because always is necessary for running or operating with conditional statements. So always begin has been written on. Then after we have if condition. If condition is true, then statement will display. Result will be displayed. Then after, if condition is not false, then another condition, means else, will be displayed. Then after we will have end of always block. So we can have we can design simple like encoder, decoder type of circuits in if statement. So let's begin with also case statement. Then after we can do an example of case. So case using case and if are quite similar, which needs always block. So you already know about that. So in case statement, we should have case and case expressions. What condition are we going to check on? So we then after we will check the condition, means expression values, like case expression value when case item 1, then it will do the operation. When value of case expression is case item 2, then you will do another statement. Then after case item 3, while value of case expression is case item 3, then it will do this. Else there will also have default case. Then after end case. Then after we need always block in in end. Then after we have module in module. So this is the basic logical concept of designing with case. So let's see an example of a case, which is the example of 4:1 multiplexer. Actually, multiplexer is many into one type of combinational circuit. So actually it takes many inputs, 4 inputs. Then after it will give to the single output. So we have 4 input ports of 8-bit wide, and selection line. Selection is the select which input to be switched on output. Then after we have 8-bit of output put also. So always block has been started. So this is the different type of stating on always block. Then we have case value expression of selection. When when SEL value of SEL is 00, 2-bit wide of binary 00. This actually signifies that 2-bit wide binary and value is 00. If this is 8-B and value will be that, that signifies that 8-bit wide binary value. We can also have a hex or decimal type of value. So when selection is 00, A in will be provided to D out. When selection is 01, B need to D out, C need to D out, and D need to D out. So this is in case, and we should have in module also. We also need default case also. We will see about this program in IC Design Suite. So let's work on IC Design Suite. So this is another example of how we can use case statement on state machine design, which we will discuss on another lecture session, another section. So let's come here. So we also have included the multiplexer program right here. So let's copy this program. So let's create new project of Mux, and what we need is Verilog module Mux. Then after we will include our program here. So this is the basic program for multiplexer. You can see. Then after we explain about this is also the program of 1995 division of Verilog. So here is selection and single bit input, and we have output of we have 4-bit wide input, while our program have different 8-bit wide input initially. So this is a little bit different than we discussed about our program. So this is quite different than this multiplexer. So these have 8-bit wide 4 input ports, 8-bit wide output port, but our 4:1 multiplexer have 2-bit wide selection line and 4-bit of input port, and output is 1 bit. So we also need register for storing or holding that output result. So we also have select wires. These wires actually provide the connection between our input and selection line. So we have always @ select or D. Actually, these are the inputs which are sensitive to our always block. So always block has it begin. So we have a case. This is the case expression, which is select. When select is 0, this is actually the decimal value. So if we like to place binary, then we should have 2-B 0 0. We can also write this instead of 0. When selection is 0 0, the 0th or LSB of input will be provided to output. As usual, MSB of input will be provided to output Q, which is actually the register. Then after it will go to port Q, while selection is 3 or 1 1. So case has been ended. Then after we should in always. Then after we should in module. So this is the basic concept of multiplexer. We can even simulate this type of multiplexer, including with test bench. So let's also begin that test bench. So we need to have test fixer. I will adjust the sim for fast approach. So it will give us a basic syntax. In the stimulus, we need to define something. So what we need here is we need to copy this selection. Initially selection is 0 and value of D is also 0. So actually we can see our D is 4-bit wide. So we should have D must be 4-bit wide binary. This will be good. Then after we will vary. Selection will be 1 and initially there will be 0, 1. We can even have, so it will give 2 main int 1, and we can copy this. We are simulating multiplexer, so this is quite different than other. So let's have final. Actually this is the decimal value and this is the binary. We can even place binary instead of decimal. I think this is good. So let's save this and let's check the syntax if we have did many mistakes. So we have some mistake here. So this is simulation program. So let's check. I think our stimulus is good. So let's simulate this stimulus. Actually we can make it zoom into the waveform. So let's click on here. The selection is 0 0 and we have little bit different result. Actually what happens here is we provide our input state in MSB instead of LSB, so we started with differently. So what we need is we need to start from LSB. So this will be good. 1 0 1. This must happen there. So while we select third means 1 1 in binary to select MSB. So in previous we have high on LSB only. So this is the correct version of our simulation script. So let's re-simulate this program. I think result will be good at this condition. So let's zoom it. So output is always high because we have provided selection of 0 0. So it will take LSB means least significant bit means 1 into out, the second bit into output, third bit into output, and fourth bit into out. This is the basic concept of, basically we already have talked about case always, and we also have idea about if statement. So we will work on that if statement again in another session, because if is highly used on designing different combinational circuits like encoder, decoder, multiplexer, demultiplexer, and we can also use case statement instead of if also, because which can be interpreted similarly. So there is some difference in syntax only. So this is the case. So you can see here the bibliography of our presentation in later. Guys, thank you for watching. We will continue on another session.